Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. In 1989, I was in the news headlines for discovering practical parallel processing as the vital technology that will underpin every supercomputer. My discovery of practical parallel processing that occurred on the 4th of July 1989 was the cover stories of oil and gas industry publications. Parallel processing was a newsworthy scientific discovery because it is the vital technology that will enable the petroleum industry to solve a grand challenge problem. Without parallel processing, a grand challenge problem could take 30,000 years to solve on a supercomputer that is powered by only one processor. I discovered that with parallel processing, a grand challenge problem could be solved in just one day and across a new internet that is a new global network of 1 binary million processors. When I began supercomputing back on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, United States, parallel processing was then considered theoretical. The technology was mocked, ridiculed, and dismissed as a huge waste of everybody's time. Parallel processing was the beautiful theory that lacked an experimental confirmation. But on the 4th of July 1989, parallel processing became reality and became so because I discovered it across a new internet that was a new global network of 64 binary thousand processors. My discovery made the news headlines because the radically different technology called massively parallel processing called for a significant change in how we compute and how we solve the toughest problems arising in mathematics and physics. Parallel processing was a paradigm shift from one processor processing alone to millions upon millions of commodity off-the-shelf processors supercomputing together and doing so to solve grand challenge problems arising in science and engineering. Without parallel processing, we will only know what might happen. With parallel processing, we know what will happen. The petroleum reservoir simulator is used to hindcast the outcomes of various crude oil and natural gas recovery scenarios. Because the production oil field is often 1 mile deep and the size of a town and has variable properties such as permeability and porosity, that oil field had to be simulated across a parallel supercomputer that occupies the space of a soccer field. The leading commercial petroleum reservoir simulators include CMG, the acronym for Computer Modeling Group. It includes Eclipse of Schlumberger, that is the industry reference reservoir simulator, that is used for black oil compositional, thermal, and streamline reservoir simulations. Eclipse is the acronym for Exploration Consultants Limited's implicit program for simulation engineering. The leading commercial petroleum reservoir simulators include Intersect, the high-resolution reservoir simulator of Schlumberger and Nexus Halliburton. The leading in-house petroleum reservoir simulators include Empower of ExxonMobil, the modular reservoir simulator of Shell, the parallel oil, gas, and water-enhanced reservoir simulator of Saudi Aramco, and the PSIM of ConocoPhillips. Parallel processing is the vital technology that makes it possible to execute the extreme-scaled computations that is the mathematical precondition to understanding the motions of crude oil and natural gas that flows across a subsurface hydrocarbon reservoir. Parallel processing makes it possible to model an oil field and do so at the microscopic rock pore scale to an oil field that is the size of a town, and even to the entire Niger Delta oil fields of the southeastern region of Nigeria. Parallel processing will make it possible to re-examine the abandoned oil fields in the Niger Delta region of Nigeria and to re-examine them under a new microscope, namely the billion-dollar supercomputer that can pinpoint new deposits of crude oil and natural gas that were formerly invisible to recover. Parallel processing changed the way we search for and recover otherwise elusive crude oil and natural gas. I visualized a petroleum reservoir as a large sponge that is buried 1 mile deep, that is the size of a town, that is filled with crude oil and natural gas that were formed 1 million years ago. Before the 1950s, only about 10 to 20% of discovered crude oil can be recovered and extracted by using primary oil recovery techniques. By 1956, the year the first oil field was discovered in West Africa, an additional 10 to 20% of that discovered crude oil can be recovered and extracted via a secondary oil recovery technique, namely injecting water into the production oil field. New techniques and technologies called tertiary oil recovery techniques that were invented since the 1970s to present make it possible to recover up to 50% of the crude oil discovered and recover it by injecting CO2, carbon dioxide. The technology that I invented, namely parallel processed extreme-scaled petroleum reservoir simulation, that is used in the recovery of subsurface crude oil and natural gas, was the cover story of the May 1990 issue of the SIAM News. The SIAM News is the flagship bi-monthly news journal of the mathematics community. The SIAM News is where the most newsworthy contributions to mathematics are reported for the international mathematics community. The combinations of primary, secondary, and tertiary oil recovery strategies make it possible to recover up to 50% of the crude oil and natural gas discovered. Put differently, recovering 50% instead of only 10%. It's like discovering 4 more crude oil deposits and doing so without actually discovering 4 new oil fields. The goal of the parallel processed petroleum reservoir simulation is to quote-unquote deplete the production oil field and do so to a priori figure out the best operating scenario that will maximize the amount of hydrocarbon recovered and yield the highest profitability. The 5 types of reservoir data are geometry, porosity, permeability, relative permeability, and fluid properties. In petroleum reservoir simulation, the dependent variables whose values depend on those of 4 independent variables are the 3-dimensional velocity distributions of the crude oil, injected water, and natural gas, the pressure distributions across the production oil field that is often 1 mile deep and the size of a town, the saturation, the chemical compositions, and the temperatures at various locations within the oil field. The complete set of equations and the auxiliary conditions form the mathematical model of the petroleum reservoir that is called an initial boundary value problem that is at the calculus and the algebraic foundations of the high-resolution petroleum reservoir simulation. The 9 partial differential equations that I invented had their origins in the motions of crude oil, injected water, and natural gas. That crude oil and natural gas flow 1 mile deep inside the production oil field that is the size of a town. The Philip Emeagwali equations are not science fiction equations. The Philip Emeagwali equations are partial differential equations that were validated by experiments and physical observations. In a manner of speaking, the Philip Emeagwali equations are mathematical caricatures of the production oil and gas fields that it governs. I am the research computational mathematician that discovered how to express in calculus terms called partial derivatives and express the motions of crude oil, injected water, and natural gas that were flowing across a production oil field. The 9 partial differential equations that I contributed to calculus are at the mathematical foundation of the extreme scaled parallel processed computational physics that completely describes the motions of crude oil, injected water, and natural gas that flowed 1 mile deep inside the petroleum reservoir. That hindcasting of fluid motions helps the petroleum engineer discover and recover otherwise elusive crude oil and natural gas. That supercomputer solution that is executed across millions upon millions of processors describes the flow patterns of the crude oil, injected water, and natural gas that is flowing 1 mile deep inside the oil field. As an aside, and as a fun fact, I have a famous photograph of myself with the partial differential equations used in real-world petroleum reservoir simulations that I scribbled on a green board that was in the background. That photograph has been reproduced in postage stamps and videos and is widely reprinted in school textbooks and reports. That photograph was taken on May 9, 1996 within the Science Museum of Minnesota at St. Paul, Minnesota, United States. The partial differential equations that I scribbled on that green board were the pressure and the saturation equations that governed the petroleum reservoir simulator that was used by Exxon Corporation back in the early 1980s. It's amusing that those pressure and saturation equations were inadvertently reprinted in textbooks for 12-year-olds. Those equations were over the head of any calculus teacher and research mathematician. Even the most knowledgeable teacher of mathematics or physics or computer science could not explain what those partial differential equations meant, and most importantly, could not explain how to parallel process and how to solve them at the world's fastest supercomputer speeds. Nor can they describe how I discovered critical errors in those partial differential equations as reproduced in textbooks. Nor can they describe how I reformulated them as the governing equations of an initial boundary value problem that I parallel processed across my new internet that was my new global network of 64 binary thousand processors.
Insightful and brilliant lecture.